Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last lecture, I introduced the idea of a metamaterial, and we talked about some of the features of a negative index material. And I said that okay, these are very interesting, and the interest in negative index material essentially drove the metamaterial research from roughly about 2000 or so to about 2010. So in this lecture, I'll go into a little bit more details of the negative index material. So the first point I want to make is we understood that we need to engineer the electric and magnetic response in order to achieve a negative index. But how do we do that? Because if you just look at the basic optical properties that we studied in the second and third weeks, we see that the material constants are essentially defined by the type of material and to some extent geometry, but in the case of metals especially, you don't see that much of an effect except if you pattern it to nanoparticles and so on. So we will try to address that. We will show you how we can actually engineer the metallic properties. Okay. The first example I'll take is a simple array of nanowires. You could think of this sort of a, the wires are aligned along the z direction, and in the xy plane they are arranged in a periodic lattice. It could be cubic, it could be, you can design the lattice. So this structure in the modern form I think was analyzed by Professor John Pendry, Sir John Pendry, in the late 90s and early 2000. But in fact, this was studied way back in 60s and 70s also in the context of RF wave propagation, and at that time they used to call it artificial dielectrics. The reason is, they considered structures something like this. For example, let's say in the 70s and 80s they wanted to engineer the dielectric response. So what they would do is simply take, let's say, R roughly in the range of maybe about a few microns. Let's say 5 microns. Okay, and then they'll take the periodicity to be very large. Okay, so in this case maybe let's assume to be about 50 nanometers. Okay, so I have, sorry, not 50 nanometers, 50 millimeters. Okay, so what I'm saying is the lattice is very sparse. You have very large extent of dielectrics, or in this case air, and the radius of the nanowire is very, very small compared to that. Okay, if you take such a scenario, you might think that, oh, what interesting things are going to happen. But in fact, I'll show you that a lot of interesting things can happen with this. And so for that, the essential point to realize is this structure consisting of rods behaves like a dilute metal. Okay, what do I mean by that? Well, we looked at metallic properties, and if let's say think about silver I believe has roughly 5, I think it is 5.8 into 10 power 28 atoms per meter cube. That is the density of silver, or the electronic density in silver. Okay, so we defined what is called as a plasma frequency. Based on that, plasma frequency was Ne square by m epsilon naught, square root of that. Okay, but now if you consider a scenario like this, nanorods, and you have light incident in the xy direction. So maybe light is incident this way. This is the k direction, k of my incident light, and then my electric field is essentially in the normal along the wire. Okay, let's say this kind of scenario. What will be the effective carrier density that the wave will experience? That's a question, right? So for that, it turns out that we can define an effective permittivity, effective electron density in terms of this expression here. So wherein my n is the original electron density here, n is the original electron density, and I'll simply multiply it by what is known as a fill fraction. What do I mean by that? Well, if I take this lattice, I can draw, let's say let's assume that it's a cubic lattice, so square. So the size, this is basically A. Okay, And then in the center I have a nanowire, which maybe I'll represent it this way. So nanowire has a certain radius, so this will be 2 times r. Okay, so I can define the extent of the area of the nanowire to the area of the unit cell. That I'll call as fill fraction. So in this case, it's only basically, two materials. Let's say this is aluminum, let's call it, and this is air. Okay, so this is a two-phase medium, we can say, aluminum and air. So in that case, my fill fraction is going to be F1 is going to be simply the area of the aluminum. I'll call it as 1, so material 1. So that will be pi r square divided by whole a square. This is my fill fraction for the metal. And of course, I can define the fill fraction for air as well, which will be simply everything else excluding the metal. But since only there are 2 materials, F1 plus F2 is going to be 1. So basically, this is going to be 1 minus F1. So this is the fill fraction for air. Okay, so I'll call this as fill fraction. Okay, so now what I'm seeing is, if I take this sort of a nanowire, I can define my effective electron density in terms of the initial electron density times the fill fraction. That will give me the effective electron density. And one more aspect that we have to realize is, now the electrons are not really entirely free to move about. There is a self-inductance associated with the nanowire, and that causes the electron to behave as if it has a slightly different electronic effective mass. Okay, and we don't need to go into the details of it, but effectively, how, if you take a wire and you calculate the inductance of it, and from that you sort of can estimate how much is this effective mass, and it turns out that it has an expression of the form which is given here. So effective mass is basically dependent on the ratio of the whole unit cell to the radius of the nanowire. So 1 over r dependence is what we will see for potentials, and you can actually do it from basic electrostatics. All right, so you have an effective mass. So now what we are claiming is, this entire medium of, let's say, wires arranged in a lattice is going to effectively behave like a Drude metal, but it has modified parameters, which are basically the effective plasma frequency, and also the effective plasma frequency. The effective plasma frequency has 2 terms. One is the effective carrier density, and then effective mass, which is different. Okay, and it turns out that this is expression that we get for effective plasma frequency. So we can compute. Let's say if you are given a metal with certain carrier density, I'll actually give it as an example for you so that you can see the impact. If you take, let's say, silver directly and a piece of silver, the plasma frequency is going to be something like 3 eV or so, 3 or 4 eV or so, right? We have calculated it in the first, second and third weeks. Now, if you just make it into nanorods, it turns out to be something much smaller. Now, perhaps this will turn out to be about few gigahertz. I'll give you this problem in the assignment. You just substitute this expression and you calculate what is the plasma frequency. That's all you need to do. All right. So, is this on? Yeah. All right. So, with that plasma frequency, I can calculate, and the standard Drude model applies. That my metal is going to behave as if, there is this effective plasma frequency. And of course, I need to tell you what the gamma is, and it can be different for different scenario. It could be some, 0.01 times plasma frequency. That's a typical low. If I take a low loss metal, my gamma will be small. Okay. So with those parameters, I'll try to ask you to calculate the plasma frequency, and you please do that. Okay. You might say, how are you defining? Because it's clearly anisotropic, right? The way the metal is, the electronic response in this Z direction is going to be different from the XY directions. Okay, that is true. So whatever I am calling here, so actually you should, if you have to define the electronic the response of this, you will have to write a tensor. The permittivity is no longer a number, but it's a tensor of the form. Let's say EXY, epsilon XY, and then epsilon. Sorry, I don't have space. It will be a 3 by 3 tensor. And since the axes are chosen such that, let me write it here. Okay, this guy is going to be represented by tensor of this form, epsilon xy, and epsilon z. Okay, so the rest of the terms are going to be 0. So 3 by 3 matrix. Because it's an anisotropic medium, in the z direction the response will be different from the x and y directions. So what I'm calling here, this effective epsilon is basically epsilon z of omega. All right. In the xy direction, we'll still have to talk about, and in effect, it turns out that it will be an average quantity. We will not worry about it right now. All right, because if you think about it, for the dimensions that I have mentioned, this is 5 microns, so 10 micron diameter to 50 millimeters. So it's 1000 times or so. So we don't have to worry about this for now. All right. Good. So this is the first example that people have looked at, as I said, in the 70s also. So this is allowing us to tune the plasma frequency. So effectively you're choosing, because for negative index, it's all about tuning the material response so that you get the desired epsilon and mu. Okay. A similar example is basically what is shown here. Okay. So this is what we will call as a planar metal dielectric composite. So essentially I can think of the similar case, in this case maybe epsilon 1 is silver. And epsilon 2, of course, you can't, if you have air, you can't have this medium. So I'll put it as a dielectric, maybe something like SiO2. Okay. Silver SiO2 composite. So I'll deposit multiple layers of these things and I can get a metamaterial like this. So this is again an interesting structure because it has anisotropic response. So now in this case, again, you see that in the plane, right? It is, the electric, suppose my electric field is in the plane like this, its response is going to be identical in x and y directions, but in the perpendicular direction, you have a response which is different. So I can define my tensor of this form. I just wrote it in the last slide. So this is my permittivity tensor. Permittivity tensor of this form. Okay. Is a tensor given by, it's already written there, so you don't need to. Okay, this is the permittivity tensor given by this. Okay, so now how do we analyze this? Well, let's first consider a situation where my electric field is parallel to the interface. Okay, so electric field is in this direction. So what will happen? Well, we understand the Maxwell's equations, we understand the boundary conditions, that the tangential component of the electric field has to be continuous. So what does it mean? So the overall electric field E is going to be equal to the electric field in, let's say, medium 1 E1 plus medium 2 E2. Okay, sorry, I should not. Electric field equal to E1 equal to E2, right? The electric field is continuous across all the mediums, so I'll call it as E. What happens to the displacement field? D. So now the displacement field has to be a geometric average. So D is going to be D. Let's say the fill fraction. Again, now we can think of fill fractions. Now the fill fraction is going to be dependent on the thickness divided by the period. Okay. So the fill fraction of the first medium into, let's say, D1 plus fill fraction of second medium into D2. So what we are saying is, we are assume the periodicity A is much smaller than lambda. Okay. And there is a certain fill fraction, F1 plus F2 equal to 1. There are only two components in this metamaterial. So F1 plus F2 equal to be 1. Okay. So now when I do this, immediately I know what is expression for D, right? D is epsilon times E. And so I can use that expression and I can say that my epsilon E is going to be equal to F1 epsilon 1 E1 plus F2 epsilon 2 E2. So from that you see that the parallel component of the permittivity is simply going to be a geometric average. Okay. So that will be given by this term here, this expression. The parallel component of permittivity is this. Now what about the perpendicular component of the permittivity? Now when you have perpendicular component, we can't write E equal to E1 equal to E2. The reason is, it's discontinuous. There can be a surface charge, right? But we know that D is continuous in the case of perpendicular component. So I can write my, let's say, D field is continuous. So D equal to D1 equal to D2. And what happens to the electric field E? Well, since my periodicity is much smaller than lambda, I'll simply define it as an average. So now my E effective, or I'll call it as E, if I just want to make it explicit, let me say E effective and also make it perpendicular. I'm just making it explicit. That is going to be equal to F1 times E1 plus F2 times E2. Okay. Once I take this, and we know what is E1, what is E2, and what is D, right? So I'll write it E effective perpendicular. I'll write it as D is basically epsilon times E. So I'll write it as epsilon effective perpendicular. Well, no, D is continuous, right? So I'll put in the first expression. So let me go back. So what I'll say is this is D by epsilon effective perpendicular is going to be F1 times D1 divided by epsilon 1 plus F2 D2 divided by epsilon 2. Okay. What I'll see is my epsilon effective perpendicular is going to be F1 divided by epsilon 1 plus F2 divided by epsilon 2. So what we are seeing is the parallel component is simply weighted average. No, this is weighted average. Okay. Whereas the perpendicular component turns out to be weighted harmonic mean. Okay. And if you have studied some basic, if you remember, the harmonic and the regular average form the bounds. If you change F1 and F2, you can have these extreme cases. Okay. So let's just take an example of, to see what it is. Let's assume that I have a metal with epsilon 1 equal to minus 10, and I have a dielectric which is simply silicon dioxide. So what will be my parallel component of the epsilon? Simply, let's assume that F1 equal to F2 equal to 0.5. Okay. If I do that, my epsilon parallel is going to be 10 into 0.5. That's going to be minus 5 plus 1.125. I think so. I think 1.125. All right. So that's my that's my permittivity in the parallel direction. Some number. Similarly, epsilon perpendicular is going to be. We can rearrange this geometric mean. That's what is given here in the top. This is my harmonic mean, right? So in this case, epsilon 1 into epsilon 2, that is going to be minus 10 into 2.25 divided by epsilon 2, that is going to be minus 5 plus 1.125. I think, if I'm not mistaken, that is it. Okay. Some number is going to come up. I don't know what it is. This is okay, minus 22. Let me leave it like this. Yeah, 22.5 divided by something here, 125, some number. Anyway, so I think this will turn out to be something in the range of 6 or slightly more than that. All right. So what you see is, just because we have taken a metal and a dielectric composite, we are able to change the permittivity in the parallel and perpendicular direction depending on the field fractions. Okay. So we have got a good amount of control on the permittivity. And we can also have more complicated structures, even random structures. There's a lot of theories that were developed in the late 80s and early 90s called as effective medium theories for the case of plasmonics, which talk about it. These effective medium theories are even older actually, the original forms. All right. So we can use that to analyze the material properties. So we can have some control on the material properties. All right. So what? This is still only telling me how to control the epsilon. What about the magnetic response, mu? How do we control that? Well, to control magnetic response, we have a very interesting structure called as split ring resonator. Okay, that's a very famous structure that any metamaterial, typically, it's a most famous metamaterial, I would say. Okay, to understand how the magnetic response can be engineered, let's simply start by considering a simple metal disc like this. Okay, I'll have a metal disc of this form, and I'll ask you a question: does this exhibit a magnetic response? What do we have to think about when we ask that question? well, does it interact with magnetic field? If I simply take a bulk medium, there is going to be some magnetic response, but it's not going to be strong. Okay. Typically, the magnetic response is much weaker than the electric response, just because the incident electromagnetic wave has the electric field, right? And it can cause a dipole moment to be created. But if you have to create a magnetic dipole moment, you will have to have a circulating current. And that is one of the reasons why the magnetic response is going to be very weak. And in fact, the magnetic response is weaker by about 1 by alpha square, where alpha is a fine structure constant. So it's quite weak, magnetic response. But if you have a disk like this, will it have a magnetic response? So now let us consider, just for analyzing this, that the magnetic field incident is in normal direction here. Okay, B is out of plane. I'll take this situation. Okay, when I take my B to be out of plane, will it have a magnetic response? Well, of course it does. The reason is the magnetic field. If I take my right hand thumb rule, my right hand is magnetic field is coming out, so I'll point out. So the it will induce there will be an induced current in the disk, so as to counter the external field. So right now my external field is like this. So Lenz's law tells us that there has to be a circular current which is actually flowing to counter this external field. Okay, so there will be an induced current of this form. Okay, so basically circular current is induced so that to oppose the external field. And that is simply going to be, this is what we will call as Lenz's law, right? We must have studied it. It tells us that the induced field is going to be opposite. Induced field is going to be opposite. The current will be created such way. So now, this sort of a response is what we will call as weakly diamagnetic. What we mean by that is, just slightly it reduces, it's going to have permeability which is not equal to 1. Okay. So mu is going to be less than 1 in this case, slightly less than 1, not really very large number. Okay. So this is how you can create a diamagnetic response. But then quickly we'll realize that if you look at, do some simulations or even think about how the electric field, the current flows in this, most of the current is going to flow on the edges. Okay. So in principle, I don't need to simply have a disk, but I can simply create a ring of this form. So I can create how do I draw a ring structure? Maybe it won't allow me to do that. So let me do this. Okay. I can have a ring of this form, bad ring, but yeah. Okay. So basically the ring will have similar response. Ring will have similar response as the disk. The reason for that is because induced current mostly flows at the edges. So I can simply cut out the central region of it and I still will not miss much. Okay. So now this sort of a ring structure will have a similar diamagnetic response, but we should also note that this is simply current flowing in a wire. So it has an inductive response. Okay. So this is basically going to have an inductive, and I'll also say non-resonant response, by which I mean, if you think about basic circuit elements, if you have an inductor, are you going to get a resonant response? Can you create a resonance? No. Because we know that if you want to create a resonance, we need to have two terms, right? If I take a resonance, simple LC circuit, right? 1 over LC. This is what we have studied. So you need to have, just an inductor will not give a resonant response. I need to create a capacitance as well, so that I can have transfer of energy from capacitor to inductor and back and forth, and it's a resonant behavior, right? At a particular frequency, it becomes really strong response. The reason we want resonant response is, if you simply have a diamagnetic response, it's not going to be very different from one, but we want really strong magnetic response. So we have to create a resonance structure. Without that, we will not be able to manage. Because remember, this is all because at optical frequencies, the response is very, very weak, the magnetic response. All right. So how do we do that? Well, I'll end up taking a structure, of this form. Instead of this, I'll simply come up with this, a ring like this, but I'll cut it. Okay. So basically, I'll introduce a split here. Split introduced to create a capacitive response. And we already said that it's going to, if I think of the magnetic field out of the plane, I'm going to have a current which is going to be flowing in this direction. So I'm going to have a charge accumulation here, plus and minus. So the gap gives you the capacitive response, and the metal gives you, metal gives inductive response. Okay. So with such a structure, I can create a metamaterial. All right. So this is a famous split ring. But if you look at the, a little bit more of detail, it turns out that it's actually beneficial to have what is known as a double split ring. That means I have two concentric split rings. So I have one split ring like this, and I'll also create one more concentric split ring. The reason I want to do that is, if you have a regular split ring of this fashion, like what we have seen, like this, and then there is another split ring, we already said that there is a capacitance here. There's a positive and negative charge. So this essentially creates a strong electric dipole, right? And this dipole can dominate the response, but so dipole can dominate, or can be much stronger than the magnetic response. Okay. So we don't like that much. So what we do is we create one more split ring, and it turns out that because of by using hybridization concepts, I can argue that the electric field is going to be opposite, and then I can have basically two dipoles. Okay, this is one dipole which is basically in this direction, another dipole which is in this direction, and the two dipoles across gaps cancel each other. Okay, so that's why we introduce, okay, a double split ring has a better double split ring has a better magnetic response, or rather the electric response is suppressed, so the magnetic response is what dominates, and that's what we do. And also there is another reason for having a double split ring. So basically the gap between rings acts as a capacitance. So in the single split ring, the capacitance is only going to come from here. But in a double split ring, the capacitance is going to come from all across here. Between the rings itself, there's a lot of capacitance that is associated with that. And it turns out that this dominates. So we prefer having a double split ring. Okay. So it has a stronger capacitance, and omega naught can be appropriately tuned. All right. So how does it look? Well, the entire split ring structure I can simply model as an equivalent circuit consisting of a capacitance and a resistance and a inductance. And this capacitance is simply going to be epsilon A by D. Let's say D is a spacing, whatever gap, in this case, the gap between these two structures, right? That's going to be my gap. And the length, there is going to be an inductance per unit length for a metal of that, for a particular size, we can calculate the inductance and we get the L. And so once we have that, we can get an expression for the resonant frequency, which is simply going to be 1 over square root of 1 over LC. But if you have a resistance, parasitic resistance, that will also contribute a small deviation from that. And it just contributes to the width of the resonance. All right. So now you get this sort of a response, which is what we would like to have, because this creates magnetic response. And it turns out that this is the most famous metamaterial that you will come across. So original first demonstration of negative index was done, I said, at RF frequencies. And you see the structure here is simply two split rings. Of course, I mean, in this case, it's not a circle, but square, but nevertheless similar response. So it's much more easier to fabricate. So you have two split rings like this, which are concentric, and the gaps are opposing. You see that? So, and you take this single unit cell and simply arrange it in a periodic fashion, and in X, Y dimensions and Z dimensions, so you get a metamaterial. And in fact, this is the first metamaterial that was demonstrated using split ring resonators. Okay. And now this was done in the year 2001 when this demonstration was done, and there is a race to actually create magnetic response at higher frequencies. So wherein they demonstrated the magnetic response at terahertz, 1 terahertz. So this was 10.5 gigahertz. So roughly 100 times higher frequency. How do we achieve response at higher frequency? Well, instead of creating large structure, make them smaller and smaller, immediately the effective wavelength reduces and the frequency increases. Okay. So this is again a same split ring resonator, but this time the geometries are roughly on the order of 2 to 4 micrometers. Okay. Or rather, I would say simply micrometers. So if you go into, this was basically, I think, millimeter square device. The moment I go to micrometers, my response goes to higher frequencies. And in the original negative index material, the fabrication was done by PCB. Just standard PCB manufacturing. You just draw the structure and then etch it, and that's it. It was simple. But the moment you want to go to higher frequencies in the micrometer scale, we have to do nano fabrication, and it becomes much more complicated to achieve these structures. But still, in the end, people have demonstrated that you can have a magnetic metamaterial up to even terahertz frequencies. And in the same year, another group demonstrated a magnetic metamaterial up to even 100 terahertz. So you see, within the span of couple of years, there is almost like a 1,000-fold improvement in the frequency, or 10,000-fold improvement, which is amazing progress that happened. But again, this time now the structure is slightly similar. You have the split ring resonators, but now the size is down to 200 nanometers. So this is fabricated by what is known as e-beam lithography, and you see already the shape is becoming slightly distorted, and there is also no space to create one more split ring in this, so it becomes harder. But this still exhibits a magnetic response. An interesting feature of this is it's polarization sensitive. Okay. The split ring resonator is polarization sensitive, by which I mean that, let's say if you have an electric field in the parallel direction to the arm here, let's say if my electric field is, let's say in this direction here, perpendicular direction, okay, in the graph I'm showing here. So what happens is, there is going to be charge separation on this and this arm, but it cannot form a current loop. So no current loop can form. Okay. So in this polarization, no current loop can form. Therefore, no magnetic response. Whereas in the when the polarization electric field is in the parallel to the across the gap. Okay. If you have such a scenario, now immediately you'll see that the current can flow in a loop fashion, and you can have magnetic response, and that is what you see here. Magnetic. So magnetic resonance created. Now I'm talking of a circular loop, right? But then how can a split ring have a loop current? Well, yeah, you have regular current in this part of the loop, but here you have a displacement current. So overall, it just forms a circular loop. All right. And that's how you see. And this is about 3 microns. 3 microns roughly translates to 100 terahertz. So you see that there is a strong magnetic response. And whenever there is a resonance, the reflection peaks, the transmission dips. This is the standard. And then 1 minus T minus R is going to be my absorption. But one important takeaway message I want to give you is, well, yeah, this split ring resonator can actually create artificial magnetism, and then you can create metamaterials. But the moment you want to do it at higher frequencies, this is still 3 micron. If I want to create a metamaterial at visible frequencies, the structure has to be much smaller, and it becomes much more challenging. All right. So to create these metamaterials at or negative index materials at visible is quite challenging. and I'll talk about how to create magnetism in the visible frequencies and visible and near air frequencies in the next lecture. Okay, so I'll see you there. So thank you so much for your attention.